So today we are going to move into talking about atomic structure, which you've talked about in science classes, including biology in the past, but we're going to still kind of review a little bit, and maybe for some of you learn some of this stuff for the first time. The first thing we need to say is, first of all, what is the atom? Atoms are the ultimate building block of all matter. So we talked about matter being anything that has mass and takes up space when we did our defining matter and classifying matter in the first part. So this means that you can't subdivide it further, and that's true in a chemical reaction. In physical processes, it is actually possible to break down atoms even further, but only in a nuclear process. The nucleus within the atom is the tiny central part of the atom. And although the nucleus is tiny, it contains most of the atom's mass, in fact, almost all the atom's mass, and all of the atom's positive charge, and that is, you might already know because it contains the protons, which are positively charged. So most of the volume of the atom is actually just empty space. It's just an area for electrons to be kind of zipping around. Now, how do we know this? Well, Rutherford's gold foil experiment in 1911 actually is what first gave us the first idea of a nucleus. He set up a piece of thin gold foil in the path of an alpha emitter. And alpha particles are just positive particles. He didn't know what they were at the time, really. It turns out they're helium nuclei, but they're given off by radioactive stuff as it decays. So those alpha particles, he kind of had this picture of the atom in mind because electrons had been discovered. And so it was believed, though, that the positive charge was just very thin and spread out throughout the entire atom. And so he thought there wouldn't be anything positive and dense enough to stop the alpha particles from going straight through. So if you look at this little yellow beam, that represents the alpha particles. He thought 100% of them would just go straight through and hit the little detector that he had set up on the other side. But what actually happened was a lot of deflection, and you can see that in the picture. These little gold beams are referring to alpha particles that got deflected and didn't actually go straight through. And so most of the beams did go straight through, or most of the alpha particles did go straight through. So that led Rutherford to believe that the atom was mostly empty space, and that positive charge that would have been stopping or repelling the alpha particles would be very small and located in the center, and that's where we get the idea of the nucleus. So this is a much more modern and almost completely modern version of the atom, the way we think about it today. The dark orange is the positive nucleus, where most of the mass and all of the positive charge is held, and the yellow is just a sort of area where electrons are zipping around. To give you an idea of just how dense and small the nucleus is, if you were to blow up the nucleus to the size of a baseball, okay, the entire atom would be 2.5 miles across. But because that little baseball-sized nucleus contains most of the mass of the atom, it would have a density of about 34 trillion pounds, okay? Because, again, almost like 99.999% of the mass of the atom is located in that central nucleus, and it's very, very small. So it would be very, very dense. Okay, so some things that you should know about subatomic particles. Again, you may know already. Proton, you can see there, is symbolized by P+. It has a positive charge, right? Its mass is about 2 × 10⁻24 grams. It's really, really small. You don't really have to know that number, but you should know that it weighs about 1 AMU, which means atomic mass units. So atomic mass units are actually devised so that we could measure really tiny things like protons and neutrons. A neutron, also located in the nucleus, is about the same size, 1 AMU, but it has 0 charge. And then, of course, an electron is negative and very, very tiny. So like less than 1/1000th the size, the mass of a proton or a neutron. Okay, some important numbers. When we look at a periodic table, I've given you a little square of a periodic table. You can always look one up on your own, and I will give you a paper copy in class. But we see some numbers here. What are the significance of these numbers? The first number we want to talk about is this whole number at the top. That is the atomic number. So if you see that 6 above carbon, that 7 above nitrogen, and so forth, that is the number of protons for that specific element in its nucleus. Okay, so that's important because that number of protons is unique to that atom. Carbon can't have any other number of protons. It has to have 6, otherwise it's not carbon. All right, if you were to do a nuclear reaction and add a proton to a carbon atom, it would become nitrogen, right? So it would no longer be carbon because it doesn't have 6 protons anymore. Another number that actually you don't see on the periodic table is the mass number. The reason you don't see it on the periodic table is because it refers to a specific isotope of an element, and we'll talk about isotopes in just a second. But mass number is how many protons plus neutrons are in the nucleus of that particular atom. So for example, you probably talked in bio about carbon-14 and carbon-14 radioactive dating to figure out how old a fossil or a tree or something is. So that 14 is the mass number. And since we already know that mass number is defined as protons plus neutrons, and we also know that carbon has the atomic number 6 up here in the periodic table, all it would have to do to figure out how many neutrons this particular version of carbon has is just take 14 minus 6, right? Because we already know protons are 6, and we already know that the sum of the two numbers is 14, so the neutrons would have to be 8, right? So again, 6 protons always for carbon, and in the case of carbon-14, 8 neutrons. Another example would be carbon-12, the much more common isotope or version of carbon, which of course still has 6 protons because all carbon has to have 6 protons. But this time, because the mass number was 12, that means it must have 6 neutrons. And then finally, I've already used the term a little bit, but what is an isotope? So an isotope is just one version of an element, and it differs from other isotopes or other versions of that element by mass number. So carbon-14 and carbon-12 are both isotopes, 2 different isotopes of carbon, because they differ in the number of neutrons, 8 versus 6. Okay, the next thing we'll find in our notes is this little, I've just given you a couple lines of this table. We'll finish up the rest in class. If we're looking at an isotope that's written this way, this is actually called hyphen notation, nitrogen-14. We already know that that 14 is the mass number, right? So protons and neutrons together. So what can I figure out in terms of proton number, neutron number, and electron number for nitrogen-14? All right, well, first of all, we said the most important number for any element is its number of protons. Nitrogen has an atomic number of 7. That's the whole number usually written above the element symbol like it is on this table. So that means it has 7 protons. If it didn't have 7 protons, it wouldn't be nitrogen. Okay, that's very important. Then we just talked about how to get neutron number. If I know the mass is 14 and 7 of those are protons, that means 7 of them would be neutrons, right? Now electrons we haven't talked a lot about, but they are negatively charged. And assuming that this is a neutral, meaning uncharged atom over here we're talking about, we're going to assume that electrons are equal to protons. So in this case, since we have 7 protons, we would also have 7 electrons. We won't always make that assumption, but for right now, that's what we're going to do. Okay, the next one we have protons and we have neutrons. So 17 protons, 15 neutrons. So which of those two numbers is more important in identifying which element we're working with? Okay, and hopefully you're thinking protons, right? Because we said the proton number is the atomic number, and that's what defines an element. So if I look at this little segment of the periodic table, I did include the element with atomic number 17 here, and it is chlorine, right? So this would be chlorine, right? And then we also can figure out its mass number. Its mass number is going to be 32, right? because it's got 17 protons and 15 neutrons, right? And then finally, electrons, we're assuming this are going to be the same as protons. Okay, so they're going to be 17 along with the protons. Okay, finally, we'll do one more and then we'll do the rest together in class. This last one, we can't really identify the element by neutrons because neutrons don't define an element. Well, technically neither do electrons, but if we're assuming this is a neutral element or a neutral atom, what do we know about the number of electrons and the number of protons? Right? We know that they're the same. So that means I have 49 protons. And once I know that, I can go to the periodic table and there it is, indium, element number 49. And so this is indium. And then the last part is to add up protons and neutrons, 49 plus 56, which is 105. All right, that's it. We'll go through the rest of the table and learn a few more things about atoms and numbers in class.